Okay. So first things first. This question has to do with crude oil, and it says crude oil contains a large number of hydrocarbons. True. Crude oil is a finite resource. That means at a point you could run out of crude oil in a particular area. So it now asks, what is a finite resource? So that's just what it means. It's limited. Okay, so that's the first one. I think these questions are quite straightforward. That's the first one. That's the meaning of finite. It's limited. It now says, what is crude oil formed? The first option for both of them are the correct ones. Okay. Moving on. It says, which type of substance is crude oil? Which type of substance is crude oil? Now, based on what we learned back then, crude oil is not compound because it's made up of several compounds. So, I mean, it's just a mix of things. So the correct answer would be mixture. It's definitely not an element. The correct answer would be mixture. So that would be the last option for number 3. And then the next one says hydrocarbons in crude oil are separated into fractions using fractional distillation. That's true. All right. So fractional distillation just involves heating. What does it say? Complete the sentences. In fractional distillation, the crude oil is heated so the hydrocarbons would evaporate. So that would be the first what do you call it? The first gap. Okay, that's the first word for that sentence. So they would evaporate, and then the fractions collect as the hydrocarbons cool and condense. So the good thing is that they can do that at different rates or at different temperatures. So that's how we are able to get the hydrocarbons. So the first one is evaporate, and the second one is condense. Okay. The next one says hydrocarbons can be cracked to produce more useful molecules. Okay, so cracking just involves breaking them down into smaller molecule sizes. It says some products of cracking are useful as fuels. So that's the last option. That's the one that would be the correct answer. Maybe should I annotate? Okay, maybe I can annotate and then I'll erase as I go. Okay, so that's the answer for it. They are fuels, nothing else but fuels, largely fuels. That's why they are called fossil fuels. In that's the term for them when you're considering global warming. Okay, so next, hydrogen gas is a product of cracking. Okay, what is used in the test for hydrogen gas? All right, so for hydrogen gas, the test is the burning splint. The burning splint. Okay, but let me just confirm that.
Wait, the burning flint is where they burn a piece of wood and then take out the flame.
Okay, is that how the burning flint test is done?
Yes.
Okay. Okay, all right. So yes, that's fine. Okay, so I'm now wondering, why did they give us two options that seem to be almost what do you call them? Synonyms. Okay, glowing splint is for oxygen. Okay, that's fine. Burning splint is for hydrogen, while glowing splint is for oxygen. Okay. All right. So yeah, let's go. What's the next one? 5.20 kilograms of crude oil contains 1.5 kilograms of LPG, liquefied petroleum gas. Calculate the percentage of LPG in 5.20 kilograms of crude oil. Of course, that would be 1.53 divided by 5.20 times 100. Okay, so we're supposed to give our answer to three significant figures. Can you help us do that with a calculator? Percentage of LPG in 5.20 kilograms of crude oil. 1.53 divided by 5.20 times 100 over 1.
In decimal fraction.
It gave you a fraction.
Yeah.
Can you make it? Can you set it in such a way to give you decimals?
29.48.
Okay. Anyway, I can't really annotate on this one, so just take note of the answer. I guess it should match with what the what do you call it? With what the mark scheme says. You have the mark scheme with you, right?
Yes.
Okay, all right. Okay. So remember, it's to three significant figures, so that's what they need it as. Okay, let's go on to the next question. Number two. Number two says the Earth's atmosphere is always changing. That's why we have weather and climate. It says gases in the Earth's early atmosphere caused changes on the Earth. Draw one line from each change to the gas that caused the change. Okay, so let's see. From what we know, I think sedimentary rocks were formed by carbon dioxide, and oceans were formed, of course, that's water. Oceans would be formed by water vapor. Does that agree with the mark scheme?
Yes.
Okay. All right. Let me wipe this off and move on. Okay. The next one shows a table. And what does it say? It says which gas has the highest percentage in the Earth's atmosphere? All right, so the highest percentage in the Earth's atmosphere, that would be Mr. Nitrogen. That's the guy that has 78%. That's a simple question, just requires you to read it off from the table. Calculate how many times more carbon dioxide there is in the atmosphere of Mars than in the atmosphere of Earth. Okay, so take note of the question. The question says, how many times more CO2 there is in the atmosphere of Mars? So number one, this question acknowledges that Mars has more CO2 than the Earth. We're not competing. That's fine. But then the important thing is to know that that's what the question is saying, and then go and look out for it. Now, the next thing we see is that on Mars, carbon dioxide is a whooping 95%. Okay, while on Earth, you just have, it's not even up to 1%, 0.04. So for you to find how many times more carbon dioxide there is in the atmosphere of Mars than the one on Earth, you'd have to divide, because they're asking you how many times more. Okay, so that's a division question. So that's going to be 95 divided by 0.04. Okay, so can you help us do that on your calculator? Let's just find out. And they said we should give our answer in standard form. But let's find out what the answer is, then we'll now put it in standard form. So 95 divided by 0.04. I even think it's something that we can do without a calculator.
2,300.
Let me see if I can quick. What did you say? 3,000.
375.
2,375.
Yes.
Okay, I hope I got that. Okay. Like that?
Yes, yes.
Okay. So to put this in standard form, what's it going to be? That's going to be 2.3. You know, standard form, the first number is always a number between 1 and 10, right? So once you establish that, you know what you're doing. Times 10 raised to power. Now, the number here could either be positive or negative, but this time you would ask yourself, what direction should it go in order to take it back to the original number? And you will see that the decimal point should move to the right-hand side, and that's 3 times. So it's a positive 3. So that's the answer in standard form. All right, are we good to go with that?
Yes.
Okay, all right. So again, I can't keep the annotation because it's going to slide in the screen. So I have to undo as we flow. Okay. Moving on. It says carbon dioxide is a greenhouse gas. True. That's why it causes global warming. That's the whole idea. It says figure 1 shows the concentration of carbon dioxide in the Earth's atmosphere from 1960. Okay, that's the time Nigeria got independence. From 1960 to 2020. Okay, the year of COVID, where we were all on lockdown. Okay, so it says concentration, the y-axis has concentration of carbon dioxide in parts per million, and we have the year on the x-axis, which is the independent variable. So the question is this: how has the concentration of carbon dioxide in the Earth's atmosphere changed from 1960 to 1920? Well, clearly, it's to 2020. Sorry, not 1920. Clearly, we can see that it has increased. There's no way it could have decreased or stayed the same. So the answer is increased, even though it was looking like curvy kind of increase. But yeah, it's increased. Okay, we roll on. The next one says cars emit carbon dioxide. Okay, so it now tells us a car emits 17.2 kilograms of carbon dioxide. Now, sometimes you wonder how this can happen, but it's true. I mean, people are inside the car and we're regularly breathing out, so it's a possibility. The next question is that there are 4 people in the car. It now says, calculate the mass of carbon dioxide emitted per person. Simple. The 17.2 by 4. And you can see the unit is in kilograms. So it's not as if you have to convert anything to grams first before you divide by 4. 4 in 17 is 4 times remainder 1. You can put your point if you like, 0.4. So that would be 4 times remainder 1. And then put the 1 in front of 2. That's 12. And 4 in 12 is 3. So the answer will be 4.3. 4.3 kilograms. So I did that on purpose mentally. Just if you can do some calculations mentally to save you some time punching things out on the calculator. So yes, that's the answer for that question, 4.3 kilograms per person. Okay, so we move on. The next question has to do with planting trees. It says planting trees helps reduce climate change. Okay, because trees use up carbon dioxide from the Earth's atmosphere through for photosynthesis, clearly. It now says, name the process. Oh, really? So I guess I've answered the question, photosynthesis. So, all right. The next one has to do with a graph. It shows the annual change in forest area in 4 different parts of the world. And then the question is, it says, give 2 conclusions about the annual change in forest area. Okay, so taking a look at this graph, what would you say? What 2 conclusions would you draw from this graph?
Africa has a positive change in forest area in ability unit. And South America has a positive change.
Okay. So
decrease in Asia and increase in Europe.
Okay. Asia and South America, right? Show a decrease in their annual change in forest area. Okay. And okay, yeah, I think that's it. The increase and the decrease. But of course, we can clearly see that there's a bigger rate of increase in Africa and a bigger rate of decrease in South America. Okay, so those are the 2 conclusions we can draw. Okay, we're still on the matter of greenhouse gases. And it says that methane is a greenhouse gas. It now says, show sources of methane emissions. Okay. Sources of methane emissions. That's places where methane, that's the methane is produced or emitted. So it now says determine the percentage of methane emissions from landfill. Okay, so what do you think we'll do to get that answer?
Add up all the rest of the percentages.
Okay, we'll add all the percentages and do what?
It should add to 100.
What?
100 minus.
Okay, yes. They should all. Okay. Okay. Yeah, from 100, right?
Yes.
Okay. Okay, that's fine. All right. So yes, that's how you do. That's how you get the answer. Okay. Okay. Moving on. It says figure 4 shows two ways, A and B, of preventing used items going to landfill. And it now says you should name A and B. Choose answers from the box. Okay, so A looks to me like recycling. Or okay, no, let me not conclude. Let's look at it. Make, use, reuse, reuse. Okay, so A is reusing while B is recycling. Okay, so yeah, I think that's how I would describe it. B involves disposing the material before it's now converted into another material. So that's B is technically the way people make wealth out of waste products that have already been disposed or thrown away. While A is more of a function of we didn't even throw it away in the first place, but we're using it for other things within the house or in other spaces. Okay, so this one has to do with an experiment. It says some types of water contain dissolved substances too, like salt. Salt could be in water, like seawater and all that. It says a student investigated a mass of dissolved solids in distilled water and in seawater. Okay, so that's the detail of the experiment. The question is, says give one safety precaution the student should take. Obviously, I think um, the use of gloves, right, should come to play. And what else? Hello, Noah, are you there?
Pardon? Wear goggles.
Okay, goggles, yes, because of for protection of the eyes. Okay, true. Okay, so yes, gloves and goggles, the safety precaution. Okay. It says the method did not give valid results. It now says which two improvements could the student make to give valid results? Okay. So let me see. Heat until, let's look at the options. Heat until the mass of the evaporating basin and contents does not change. Okay, I think this one is a standard because it's probably trying to measure the weight of those dissolved solids. So yes, he will have to heat it the until the mass of the basin and contents does not change, while he's busy gauging the masses at regular intervals. So I think the first one will be there. It says leave some water in the evaporating basis. I don't think so. After heating. Um, what else? Record results in a table and plot a bar graph. Okay, that's expected. So yes. Um, and then it says use 25 cubic centimeter of water for each experiment. Okay. It says use a beaker instead of an evaporating basin. Okay. So which two seem most likely to be correct to enable the student to have um, um, better results or valid results. Okay, so I think the first one and the last one should do. I'm just thinking. Um, what does the mark scheme say?
Um, the first one and
Okay.
use 25 centimeters of water for each experiment.
Okay, they use 25 cubic centimeters, right?
Yes.
Okay, that's the second to the last. Okay, all right. So let's see. A different student used a method which gave valid results, okay, and was able to come by this table. It says that the student concludes that distilled water is pure, and it now says suggest one reason why. Why is distilled water pure? Is that the question they're asking, or they're asking us why the student came to that conclusion? Okay, so you know what you do? I think we can look at it from two sides, but then it's the mark scheme that will ultimately uh, tell us which one they meant. Because now I can, I'm interpreting this question in two ways. The first way is suggest one reason why distilled water is pure. So that's one way of interpreting it. And the second way is suggest one reason why the student came to that conclusion. So what I'm seeing here is if it were the second one, to suggest one reason why the student came to that conclusion, we can see that the the uh, weight in grams or the mass in grams for dissolved substances or dissolved solids is 0 on each count. So that should be a sufficient reason. But let's see what the mark scheme says. What does it say there?
Um, no dissolved solids in distilled water.
Okay. Okay, so that's it because of the mass, right? Of solids and dissolved. No the 0 mass. Okay. All right. The next question says that tap water is portable. One step in producing portable water is sterilization. Why is potable water sterilized? I think I'll go with the middle one, to kill bacteria. Potable water should not have any taste in the first place. So, mm, yeah. Okay, so we're good with that option, right?
Yes.
Okay. All right. So moving on. It says chlorine. Sorry, I put that too. It says chlorine is used to um sterilize water. It says the reaction between chlorine and water is reversible. It now says complete the sentence. Equilibrium is reached when the forward and the reverse reactions occur at the same, the answer should be rate, okay? It's at the same rate. Or, someone might say speed, but, it's reactions. So the key word there is the word rate, as in R-A-T-E. Okay? Okay. So you got that, right?
Yes.
Okay. Okay. So the next one is a test for chlorine. Test for chlorine uses damp litmus paper. So the question is this: when damp litmus paper is put into chlorine gas, the litmus paper turns. Now, ideally, the blue litmus paper turns white. It turns white. So I think they deliberately put blue there and green just to confuse us, but we know that it turns white, and the reason is because of the bleaching action of chlorine. Okay, so remember that chlorine has bleaching action. That's why it's you can find it in most bleaching agents used for washing clothes. Okay, so the next one is there is evidence that adding fluoride ions to drinking water reduces to decay. Okay, yes, so fluoride. We find fluoride in toothpaste too. So the question is this: it says figure 6 shows the percentage of people showing tooth decay. Okay, the older citizens seem to have it higher. Water with fluoride ions. Okay, these ones drink water with fluoride ions, and then the ones that are gray drink water without fluoride ions. Okay, so somehow it reduces the incidence of tooth decay in each age group. Okay, so the question is this: compare the effects of adding fluoride ions to drinking water on tooth decay in people between the ages of 25 and 74. Use data from figure 6. Okay, so what conclusions can you draw on this, on the effect of adding fluoride ions to drinking water on tooth decay?
Um, Fluorine reduces tooth decay.
Okay, it reduces tooth decay, right?
Yeah.
Now, did you notice something? It it reduces tooth decay at a higher rate in some age ranges, if you look at it, than others. Did you notice that?
Yes.
Okay, so if you look at 55, 45 to 54 and 55 to 64, you will see that um, um, there's higher reduction in those um, what do you call it, age categories. Okay, well, nice reading of the graph. Okay, so we move on now. It says that student A says that water companies should add fluoride ions to all drinking water Student B disagrees. It says, suggest one reason why student B may think that fluoride ions should not be added to all drinking water. Can you suggest why?
Could it be a risk of health?
Okay, risk to health. Okay, particularly what risk would that be?
Um, um, disquality.
Okay, so um yes. So the question now is, yes, fluoride ions show a great impact on reduction of tooth decay. But I think there's something else that can happen. Fluoride ions, high fluoride levels, if it's really high, can cause what is called dental fluorosis, that causes white patches to form. That's the covering, the part that protects, supposed to protect the tooth from tooth decay. And then, of course, there are some other possible risk factors ranging from stomach cancer to, other things. Anyway, so yes, you are right. Health reasons um, would suffice. But then, if you want to be specific about the health reasons, you may want to mention dental fluorosis and maybe stomach cancer, while student B maybe suggesting that. Okay, okay, so we're moving on now. It says a catalyst is used to increase the rate of decomposition of hydrogen peroxide. Okay, and hydrogen peroxide decomposes to produce water and oxygen. True. It now says write a word equation for the reaction. Oh, I mean, there's nothing to write. Just write. It's like just repeating the same thing. Hydrogen peroxide will be on the left-hand side before the arrow. And immediately after the arrow, you can now say water plus oxygen. That's all. Since they said word equation. Now, I don't think I've seen anywhere they asked you guys for chemical symbols. But if I don't think that's going to happen. But if it does happen, then this is what would play out. Instead of word equation, this is what would play out. H2O2 is going to give you water. H2O plus oxygen, O2. And now, of course, the equation is not balanced. So to balance it, I would have to put 2 in front of this and 2 in front of this. So that will balance everything out. Okay. So this is what would have happened if they had said chemical equation or equation with chemical symbols instead of word equation. But if it's word equation, just put their names as they've written it here. Water and oxygen, no big deal. Okay, so let me, okay, we're moving on now. Okay, so next it says, A student investigated the rate of decomposition of hydrogen peroxide using three different catalysts: manganese dioxide, copper oxide, and zinc oxide. It now says this figure shows the apparatus. What's the next question? And then the method is reeled out there. It said mention two control variables that are okay. So what do you think would be the two control variables for this case?
Shape of flask.
Shape of flask. Okay. 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 What would be the second one?
Mass of catalyst.
Mass of catalyst. Okay. Okay. Now, okay. I think I agree with shape of flask because, okay, so ideally, right, a control variable is one which is intentionally kept constant, right? So that it doesn't influence the outcome. Catalysts ideally are not even supposed to take part in a reaction. So, well, yeah, we can say that. But yeah, let's stick with shape of flask and um, yeah, mass of catalyst. The other ones are likely to influence the reaction, which is hydrogen peroxide and volume of oxygen produced. Yes, those ones are likely to influence it. But I'm thinking that time of taking readings might also be a control variable. But they said only 2 boxes, so we can't have 3. So help me check the mark scheme. What does it say for this question? Let's just be sure.
Volume of hydrogen peroxide solution.
Volume of hydrogen peroxide solution. Okay. Okay. Then the second one would be what?
Mass of catalyst.
Mass of catalyst. Okay, that's fine. Okay. Okay. Oh. That's true. So you know what? I just looked at it carefully now. You know, when I looked at that phrase, shape of flask, so my mind went to the shape of the flask would affect the volume, but really, shape of flask doesn't have anything to do with the reaction, right? Because the flask could be shaped in any way, and that would not change how the volume would be. But then if we intentionally look for how to control the reaction by making sure that the volume of hydrogen peroxide is constant, then yes, I think we've achieved that as a control variable. Okay, all right, that's fine. Okay, so we're moving on. This one says, gives us a table and a graph that is drawn. The question is, what? You should plot the, okay, draw a line of vertices. Okay, I guess you can do that, right? You can plot the data from the table on the graph.
Yes.
Okay, okay. All right. The question is this. Which is the best catalyst? So now, I'm not sure, can we really conclude on this? Can we really conclude on this? Now that I'm looking for, was there a table that was given? I'm wondering what you are even going to use and plot. the graph for, oh, okay, table 3. Oh, table 3. 1 minute. Let me see if there's anything that can give us. Okay. No, nothing here to give us any clue as to what would typically happen with manganese. You should plot the graph, plot the data for manganese dioxide catalyst from test field. So I'm just looking. They did not provide any table with values for us to draw. But I guess those will be supplied in the question, right? 3 shows the results. Table 3 shows the results with manganese dioxide catalyst. Okay, that's fine. Okay. All right. So you know what? We've not done the graph, but this is what I'm thinking. Manganese dioxide would be probably the best, right? But let's see. The best catalyst for, okay, yeah. I think it's manganese dioxide, but did they ask for a reason? It says give one reason for your answer. Well, a catalyst is supposed to speed up a reaction, isn't it?
Yes.
Supposed to make it faster. So manganese dioxide does just that by virtue of its graph. Now, how do I know? I know that you've not plotted the graph, but how do I know that the graph for manganese dioxide is going to have a bigger gradient? Well, if you look at the 2 points that were plotted for you, you can see, let me see if I can annotate to show you what I'm talking about. Here, this is the first point, and this is the second point. So what that tells me is that manganese dioxide's graph will look something around, it will look something around here. And I'm purposely not joining the 2 points because the question is saying that its line of best fit. So that means that some points will fall on this side of the line, some will fall on this side of the line, and some will fall on this side. You know, I'm not accurate with this, but I'm just presuming because it said line of best fit. A line of best fit is usually a line that goes between the points in your graph. It's not a straight line graph, but it's expected to be a straight line graph. So what we do is just to draw the line in between the points. Now, when you draw a line like this, you can see clearly that the gradient is higher than the gradient for copper and the gradient for zinc. So, and gradient usually suggests speed, right? It suggests speed. So that's why I would say that manganese dioxide for the next question. The next question. Sorry, let me take this out so I can scroll. If not, this thing won't let me scroll. So for the next question, where it says give a reason for your answer, it's just the fact that the rate of reaction is faster with manganese dioxide. Okay. All right. So we can move on, right?
Yes.
Okay. Okay, so the next question says, the student repeated the investigation with manganese dioxide catalyst. The results were all close to the true value. It now says complete the sentence. Choose the answer from the box. It says close to the true value. Results that are close to the true value are what? Approximate, right?
Yes.
Or, okay, yes, since they are close, I mean, we should go with approximate.
Accurate.
Accurate.
Yeah,
because they are okay. Did you say accurate? They're as close to the true value as possible, right?
yes.
Okay. Okay, no problem. We can go with accurate then. Okay. So the next one is oh, okay. This is at a higher temperature. Okay. So now temperature is now brought into the picture. It now says complete the sentence. Choose the answer from the box. At a higher temperature, the rate of the reaction will, I think the rate will increase. What do you think? What should it be?
Um, increase.
Okay. Okay. Does the mark scheme agree with us on that?
Yes.
Okay. Okay, so I'll move on. All right. So it's increased, that is the answer. So this is the next question. Let me just be sure. Okay. The next question says, the combustion of fuels is a source of atmospheric pollutants, true? Because definitely those fuels will yield carbon dioxide or carbon dioxide and water. It now says methane is a fuel. Question, balance the equation for the combustion of methane. So can you help me balance this, Noah?
Yes.
Okay, go ahead.
A 2 in front of the H.
On the right hand side.
Yes.
Okay, good. So it's 2 here. Yeah.
On the other side.
So that was hydrogen 4. Then what next?
And a 2 on the other side as well.
Oh, excellent. Yes, you're correct. A 2 on this end. Okay, that makes it complete, right? So that's 4. 2 plus 2, 4, 4, 4, 1, 1. Excellent. Okay, nice job. Well done. Well done. Well done. Okay, so the next one says many fuels are mixtures. Okay, for example, petrol and diesel are mixtures of hydrocarbons. It now says table 4 shows properties of petrol and of diesel. Question, compare the properties of petrol and diesel, and then it says use table 4 to do that comparison. Okay, clearly you can see that petrol is more volatile than diesel. I mean, you can see the temperature at which it will change to what do you call it? Um, vapor. Okay, so if you even, let's just say you take the lower ones, 40 for instance for petrol, and 250 for diesel, you see that, I mean, sometimes when you're under the hot sun, right, the temperature can get up to 40, as in you're outside though, under the hot sun. Now just imagine that there's a box or a gallon of petrol somewhere, somewhere. You can see that that petrol would evaporate very easily. It doesn't even need to be, you don't even need to apply any heat to it. It will evaporate. So I think it's safe to say that one of the things we can conclude from here is that petrol is more volatile than diesel and has lower boiling point compared to diesel, right?
Yes.
Okay. All right. The next one is talking about um, gases that are released when a fuel is burned in car engines, and it's telling us what they may include: oxides of nitrogen, carbon monoxide, obviously, that's the chief culprit, and water vapor. Okay. And I think I can safely say here that that's the reason why if you want to warm a car, like, warm the engine of a car, it's always advised that you do it in an open space. Okay. So for cars that are parked in a garage, you don't warm the engine with the garage door closed or shut, because that would be risky. Before you know it, all the oxygen in that enclosed space would be sucked out by the carbon monoxide, making it very, very poisonous for humans to be breathing in carbon monoxide or carbon dioxide in the first place. Okay, so what question are they saying? What question are they asking? It says, which chemical elements do all these gases contain? Obviously, it's oxygen. I can see that's common. Water vapor is H2O, so it definitely contains oxygen. Carbon monoxide is CO, so it contains oxygen. Oxides of nitrogen has even given itself away. Oxides are compounds that are formed when an element combines with oxygen. So the common denominator for all of them is oxygen. Okay, so you got that right?
Yes.
Okay, moving on. When diesel burns in car engines, oxides of nitrogen are produced. Okay, it says, where does the nitrogen comes from? So can you guess where the nitrogen comes from?
Pardon?
Can you guess where the nitrogen comes from? Where does the nitrogen come from? Because the
Where?
nitrogen, yes,
Um, there.
the air, thank you. It's in the air. So it just naturally in that heat, the heat of the engine, it would safely combine with oxygen and burn to form nitrogen oxide, or something. Okay, oxides of nitrogen. Okay, so the next question, it says, when diesel burns, particulates may be produced, particles, okay? And it says, what environmental effects do particulates from burning diesel cause? Well, what effects? I think it's largely pollution, right?
Yeah.
Okay. Are there any other effects?
Um, uh, it can affect global. Uh,
Okay, what did you say? It could affect what?
that could cause global warming.
Okay. Okay. So yeah. So I think the main thing is the fact that it's what do you call it? Pollution. It causes it's pollution, and that could be harmful to the health. Okay, so let me see. The next question says, carbon monoxide may be produced when diesel burns. True. It says, give one reason why carbon monoxide is difficult to detect. Okay, so yes, I think when you were talking about particulates, right? You mentioned um, respiratory problems, right? Hello, Noah.
Yes, sir.
Yes, did you? I just wanted to be sure.
Um, pardon?
No, I said that I wanted to be sure. Did you mention that particulates could cause respiratory problems?
Yes, yes.
Okay, okay. All right. Okay, so let's go to the next question. It says carbon monoxide may be produced when diesel burns. Give one reason why it is difficult to detect carbon monoxide. Okay, well, I mean, gases usually stem from their physical properties are usually what helps them to be detected. Now, number one, carbon monoxide, and that's why it's a silent. Sometimes people call it a silent killer. Um, Number one, carbon monoxide is colorless. Can you see the problem? It's colorless. So it can be right in front of someone and they're not seeing it. The fumes coming from a car's exhaust sometimes have color, but it's not just carbon monoxide that is coming out at that time. The real carbon monoxide can be colorless and it will look so harmless, like nothing is in the air, but it's slowly draining away oxygen especially in an enclosed space. The next thing to say about carbon monoxide is that it's odorless. So it doesn't even have a smell for somebody to tell that there's carbon monoxide coming out. And finally, is tasteless. So even, I mean, even taste, it doesn't have taste. Okay. That's and taste usually for a gas would happen when maybe somehow the gas gets in contact with saliva and it somehow dissolves in saliva, then we can manage to like taste it per se, because saliva needs, I mean, the taste buds need something that they can detect to be in liquid form. So if this thing, if carbon monoxide is tasteless, then that means it can be in the air and people will not even know. That's why it's difficult to detect and dangerous too. Okay. So the next question here says, explain why water vapor and not liquid water is produced when diesel burns. Can you explain that?
Yes.
Okay, so go ahead. Let me hear you.
Damages to the building.
What did you say?
Damages to the building.
Okay, so the idea is why or rather, the question is saying, why is it that water vapor forms, not liquid water? Yes,
sorry.
that's the question.
Sorry.
Okay.
Diesel burns at high temperature.
Yes, at a high temperature, correct. So yes, it will change any water that's any liquid water that would have been liquid will be turned to water vapor or turned to steam. You're correct. Okay, so moving on. Sulfur is a common impurity in diesel. Okay, explain why this causes an environmental problem.
Damage to aquatic life.
Okay. So you remember, I didn't hear you. Did you say damage to what?
Aquatic life.
Okay. I'm not sure I really heard you back there. Okay. But remember, it's environmental issues that we're looking at now, right? The primary causes, well, I think that the particulates that we talked about that come from burning of diesel, sulfur somehow is also a, what do you call it, a culprit too, because it can cause pollution, atmosphere, air pollution. And of course, you remember how CO2, once it goes into the air, can form acid rain. Sulfur too can easily form its own version of CO2, which is SO2. And that also can form acid rain, you know, which is not good for plants and animals too. So yes, air pollution and acid rain, all these are effects of sulfur on the environment. That's why it's an environmental problem. Okay, so you got that right?
Yes.
Okay. Okay, moving on. It says chromatography is used to separate mixtures, of course, based on color and different speeds of movement of those mixtures within the medium, usually filter paper. It now says chromatography involves a mobile phase and one other phase. Okay, so the question is, what is the other phase in chromatography? What's the other phase in chromatography?
Stationary.
Okay, so you're choosing stationary because it's the opposite of mobile, right?
Yeah.
I think that would make sense by far. Yes, I'll go with stationary too. Okay, so yes, remember the whole idea of chromatography is that what? The mixtures, the component of the mixtures will show themselves. How? By separating from each other, by moving at different speeds. Okay, so that's the whole idea why chromatography enables the the substances that are in the mixture to show themselves and expose themselves is by their different rates of movement. So at the time they move, that is the mobile phase. Then by the time they now become still and stop moving, that's the stationary phase. Okay, so of course, I think we have answered this question indirectly. Why do the substances in the mixture separate in the mobile phase? It's simple. They move at different speeds. Okay, if they didn't move at different speeds, it would have been hard to find. You understand? But because they move at different speeds, it's easy to find. One will move really, really fast and go far. That one will expose itself. While another one will move a bit slower and may not go that far and stop. So yeah, you will now see two different colors. The first one that moved really fast up to the end, and then the second one that didn't move that far and that fast. Okay, so it says how many spots will be produced on the chromatogram of a pure compound. Okay, so now I mean, what do you think? If something is pure, I mean, that means it's not a mixture, isn't it? A mixture suggests something mixed with something that is, like an impurity, right? Or something that is a different substance. That will make it a mixture. But now, if it's a pure compound, then there will be nothing to separate from another. And so that's why a pure compound will just have one spot. Do you agree with that?
Yes.
Okay. All right. Okay, so there's a question here that has a bit of a calculation, and it says, in a chromatography experiment, a blue color moved 4.77 centimeter. The solvent moved 4.30 centimeter. That's the solvent. Question is, calculate the RF value for the blue color. Okay. RF value, I think that is the substances distance divided by the solvent distance. Let me confirm that, please. Okay, so let me see. Okay, okay, yes, so that's it. Yes, it's correct. In the RF value, you divide the distance traveled by the component by the distance traveled by the solvent. So yes, that's correct. So we're going to divide 4.77 by 5.30. What does that give you on your calculator? 4.77 divided by 5.30.
0.9.
0.9. All right, thank you. So we're moving on to the next question. It says black ink is a mixture of several colors. Plan an experiment using paper chromatography to separate the colors in black ink and then identify the colors from their RF values. Okay, so I'm sure you'll get the details in the mark scheme of the process, but let me just say a few things about it. Number one, you only use organic solvents for organic mixtures. Okay, let me say that again. You only use organic solvents for organic mixtures. That means that, for instance, something like the ink in your pen, a typical pen, It's usually oily in nature. I don't know whether you've noticed it before. Have you ever used your, those days when we would try to fix our biros, and somehow we'll end up messing up our fingers with the ink. Have you ever felt the texture of ink that's from a pen before? You see that it's a bit oily in its content. So it's organic. And because it's organic, most likely the things that you would use as solvent would be something that would work very well, would be something like petrol, or kerosene, stuff like that. That's the only thing that those kind of organic solutes or mixtures will dissolve in. So that's the whole, that's what I wanted to say here. So for this black ink, definitely it has to be something that the solvent has to be something that is also organic, which means it can be petrol or kerosene. No, petrol is not good because it could be volatile, and then if you are trying to do an experiment with it, you will not be able to get accurate values of your or accurate, yes, accurate values in your experiment. So kerosene is usually a good alternative. Kerosene, or there's another one they call paraffin oil or something. So those are good solvents for black ink, if for you to be able to see, because guess what? If the ink doesn't dissolve in the solvent, how will it separate? The aim of the solvent is to do what? Break it down, to allow it to what? Break down into its component parts. Then, of course, don't forget that filter paper must be somewhere in the mix. It's filter paper that's white filter paper, that you'll be able to see, oh, these colors have traveled far from themselves. So usually it's white filter paper so that you can see the colors clearly. Just imagine if you use a filter paper that already had another color, it would somehow interfere with the color of one of the components of that ink. Okay, so critical things: white filter paper soaked in the solvent, and then after you've already dropped the ink in it. So I'll leave the rest to you to read up from the mark scheme. Let's move on. Oh, and it appears that that is the last question. Oh, awesome. I thought there were more questions from this thing. Okay. Okay, do you want us to look at another one to make up for time left? Hello, no, are you there?
Yes.
Okay.
I'll send you another paper.
On WhatsApp?
Oh, yes.
Okay, all right, go ahead. Okay, okay, I've seen it. Okay, November 2021. Okay, yeah, let's read it. Let's open it. Okay, all right. Opening it up in a minute. Okay. Okay, let me share my screen.
When he walks through the doors. And trust me, it's not even in the like that. The mom is average height, the dad is also
Okay.
average. There's nothing
Confirm that you can see my screen now.
bad with that height.
Can you see my screen? Noah.
Yes.
Yes.
Okay, good. All right. Okay, so let's look at the first question. It's about fresh water. It says fresh water contains low levels of dissolved salts, yes, compared to seawater. The question is this: water reacts with anhydrous copper sulfate in a reversible reaction, okay? And then what does it say? The word equation for the reaction is water plus anhydrous. Please remember that the word anhydrous means it's dry, okay? That's anhydrous, no water in it, it's dry, okay? All right. So the next question is, how does the equation show that the reaction is reversible? Okay, how does the equation show that the reaction is reversible? Well, a reversible reaction simply is one that the products, the reactants can come together to form the product, and then the product can either decompose or break down to give you back the reactant. So that's the only way I can explain it. Okay, that's how the equation is reversible. The product in this case is hydrated copper sulfate. It can be broken down again to form anhydrous copper sulfate and water. So it's reversible in that sense. Okay. So what's the next thing? It says choose answers from the box. Okay, so what do you think will be the answers in this case?
Um, White.
White, okay. So that's for anhydrous copper sulfate. Okay. Then when water gets into it, what happens? It turns what?
Blue.
Blue, correct. Yes. In fact, that's the what do you call that color now? That's the characteristic color of copper when it's reacting at a higher state, or when it's in a higher state of a higher energy level within its orbitals. Okay, so it says figure 1 shows anhydrous copper sulfate in a sealed container. It now says suggest one reason why anhydrous copper sulfate is kept in a sealed container. Can you guess why?
It reacts with oxygen.
It reacts with the
With the air.
water vapor in the air. Yes, the water vapor in the air, not really the oxygen per se, but the water vapor in the air. So it's quickly, just from what we just discussed now, it quickly reacts with water vapor in the air. So that's why it has to be sealed so that it doesn't react. Okay. So the question on this page says, Sodium chloride dissolves in water to form sodium chloride solution. The question is this: draw one line from each substance to the description of the substance. Okay, so sodium chloride solution is simply, it's not, I would call it a, do I call it a compound? I think it's safe to call it a mixture, right? Because compounds form as a result of, what do you call it? As a result of a reaction. So things will change. You know, one atom will go and react to the atom of the other one. But that's not what happens in sodium chloride. It dissolves. It just dissolves. So this is what I'm going to do. I'll draw a line from sodium chloride solution to mixture, and then, yes, I can put it back on that question, on that answer, sorry. I don't know. Are you with the mark scheme there?
Yes.
Okay, so does it agree with us?
Yes.
Okay, all right. I just wanted to be sure before I dismiss this. Okay. Sorry. All right, moving on. It says two processes used to obtain potable water from fresh water are: number one, filtering, that's with using a filter paper or a sieve, you know, if a sieve with very tiny holes, okay. Then sterilizing, of course, that's boiling it. And boil it or use chlorine, anyone, to bleach it. Okay. It says give one reason why each process is used. So filtering will remove little particles, right? Will remove impurities that are in form of particles, while sterilizing will take care of the bacteria. Do you agree with that?
Yes.
Okay. All right. So the next question says, which type of water is the easiest to obtain potable water from? Which one do you think would be the correct answer?
Um, Ground.
Did you say ground or salt?
Ground.
Ground. Okay, why did you say ground? Because I was thinking that you would go for salt.
Said easiest to obtain, and groundwater is usually
Okay.
most likely to. Yeah.
Okay. Okay, so yes, you are correct. Now ideally, right? For ground, there's this what they call it, level of filtration technique that uses stones and all that to filter water. And if you put groundwater and make it pass through that filter, it will filter it so clean that you would wonder if that was really possible. But then with salt water, for you to get potable water from salt water, you would have to boil it till what do you call it? Boil the water till it boils and completely boils. And then you have to look for a way, not just to boil it anyhow. You have to look for a way to prevent it, to prevent yourself from losing the water. So you would need, maybe some apparatus like that that will help you collect the water vapor and into another container, So it involves a lot of hassles, and stress. In that case, you would need more equipment, but groundwater can easily be filtered without even boiling anything. You don't need gas, you don't need any source of heat and all that. So we'll go with, I also agree with groundwater. Of course, nobody's even mentioning wastewater because that one is on another level of purification that you need to get it pure, to make it pure, rather. The next one says, which of the following is the first stage of wastewater treatment? Okay, so which one do you think is the correct answer for this guy? Or you could just, what did you say?
Is the last one.
The first stage, the last, did you say the last one?
Yes, the last one.
Okay, screening and removal of grit. Okay, that should be it. Yes, I think I'll go with that too. Okay. Okay, the next one gives us a fact there, which we know is obvious. Cars cause atmospheric pollution. What next? It says figure 2 shows the percentage of cars in the UK using different energy sources. Okay, diesel, electric, petrol doesn't even seem to show, and other. Okay, so that means more cars of, I said, oh, okay, sorry, they didn't just show it on the graph. Okay, obviously more cars will use petrol. I started wondering why petrol didn't show. Okay, so it says percentage of cars using petrol is 54%. Draw the bar for petrol. I guess you can do that. You can do that. This one is 1 unit, 1 cm to 10 units. So that means each box is 0.2. So yes, petrol would be something like this. Let's see. Okay, there are 6, okay, in between. So 1, 2, 3, 1, 2, 3. So it will look something like this. Okay, so I guess you'll do a better job than me if you use your ruler. And then how many boxes are there? We have to make sure that there are also 3 here. 1, 2, 3, 1, 2, 3. Okay. Okay. Sorry about that. And then there. Okay. Yeah. So that will be the box for petrol. So that means more people use. So the next one says some car emissions contain nitrogen dioxide. It says table 1 shows the concentration of nitrogen dioxide in the air in 3 different areas for 1 week. Okay. Question: which column of data has the greatest range? Which column of data has the greatest range? Now, remember what I told you about range. Range is the difference between what? The highest and the lowest. So, I mean, it's obvious that countryside has the lowest range, right? Because the difference between 8 and 7 is 1. That's the lowest range I can see here. For motorway, the highest seems to be 23 and the lowest seems to be 17. And 23 minus 17 is what? 23 minus 17 is 6, isn't it?
Yes.
Okay, so it's obvious that the guy that seems to have the highest range is city center, because the highest is 37 and the lowest is 22. That is clearly the highest range here, if you ask me. So I'll go with city center. Okay. So next, explain why the concentration of nitrogen dioxide in the air is lower on Sunday. Come on Sunday, fewer people are out there, right? It's not like a work day. Okay. Are there any other reasons you would like to suggest? Hello, Noah.
Yes.
Are there any other reasons you'd like to suggest for why nitrogen dioxide in the air is lower on Sunday?
Fewer people working. Like fewer people.
Okay, yeah. On the road, right?
Yes.
Okay, that makes sense. Yes. Okay. So the next one says calculate the mean value for the concentration of nitrogen dioxide in the air in the city centers from Monday to Friday. Okay, so that one is easy. All you need to do is to add up all the numbers in city center. 35 plus 37 plus 37 plus 34 plus 37 plus 29 plus 22. After adding them up, you now divide by 7. Okay, please don't forget, mean is simply adding things up and dividing by the number of those things that you added up. Okay. Okay, so did you get that?
Yes.
Okay, all right, moving on. It says nitrogen dioxide is removed from car emissions by catalytic converters. It says which two of the following are correct statements about catalysts? Which two of the following are correct statements about catalysts? Okay, of course, we know that catalysts, they are not included though. They're not included in the chemical equation for a reaction. And the reason is simple. They are not involved in any reaction. They simply speed up the reaction without getting involved in it. So number one option is wrong. Don't choose it. Catalysts are not used up in a reaction. True, they are not. So we'll take that. And then we're looking for the second one now. Catalysts decrease the surface area of reactants. No, I think I'll go with the fact that they lower the activation energy of a reaction. Yes. So the first one is catalysts are not used up in a reaction. And the second one is catalysts lower the activation energy of a reaction. That's even why they make the reaction to proceed faster and form the products on time. Okay. So I hope you got that.
Oh, yes.
Okay, good. The next one says the catalyst in catalytic converters contains platinum. Okay. And platinum is an unreactive metal obtained from the Earth's crust. It says what? Platinum is a finite resource, it's a formulation, it's a renewable resource. Well, clearly, if it's found in the Earth's crust, then it's definitely finite, right? The platinum reserves in a place can be exhausted. It's possible. It's not a renewable resource. It's not a formulation. It's a finite resource. Okay, are you good with that?
Yes.
Okay. Emissions from cars that burn fossil fuels contain carbon dioxide. Yes, true. It now says what is used for the test of carbon dioxide. Now, you remember we said burning splint is for hydrogen, right?
Yes.
glowing flint is for oxygen. Therefore, the only one that is left here that will help us to test carbon dioxide is lime water. Now, how do you know that carbon dioxide is present in a stream of air that's introduced into lime water? So the experiment, I think the experiment is usually that you hold a straw, you put a straw to your mouth, and then you blow out bubbles from your mouth. The whole idea is that the air that you're blowing out from your mouth will definitely contain carbon dioxide. Blow some air from your mouth through the straw into the solution of lime water. It will bubble the lime water, and the presence of carbon dioxide will show by making that lime water turn milky. Okay, so it will become milky. It's because of the formation of another compound inside the lime water. So that's how you can identify the presence of carbon dioxide. Okay, so they're not interested in the experiment anyway, but I just felt I should add that in case you come across it in the exam tomorrow. Okay, it says an increase in greenhouse gases. Now, do you know, can you give me a definition for greenhouse gases? Not that they will ask you, but at least let me just see that you have an idea of what a greenhouse gas is. What's the definition of a greenhouse gas? Or let me say, what do greenhouse gases do?
They trap
Okay.
the
They
heat in
trap
Earth's atmosphere.
heat. Okay, yes. They trap the heat that's that's radiated by the Earth's surface. So by trapping it, they make the Earth, just like this question is saying, the fact in this question, they make the Earth's atmosphere to become warm, or, to increase in global temperature, which would cause a lot of things like melting of icebergs and stuff like that, and irregular climates and things like that. So yes, so once we have that idea, you know what a greenhouse gas is. Now, examples of greenhouse gas are the ones that we all know: carbon dioxide and which other one? Methane, right? Those ones are the natural ones. The ones that are not natural, the artificially produced ones, the ones that come from man's activities, are CFCs. That's chlorofluorocarbons, and then HFCs, which are hydrofluorocarbons. So don't forget that. Just remember that there are natural greenhouse gases and artificial greenhouse gases. Those ones are produced by man's activities. So here it says an increase in global temperature is a major cause of climate change. It now says give two effects of it. So, I mean, you can mention what we said. Of course, I don't think it will be helpful to mention increase in global temperature, but we can say for sure what climate change can cause, right? Melting of icebergs, right, at the North Pole and South Pole, which can now lead to flooding, because, just imagine, one iceberg melts because of its size. It's definitely going to increase water levels, and then that can cause flooding. That can lead to flooding in areas where we didn't have, where flooding won't have normally occurred. So yeah, I guess there are other things that um, you could talk about. Um, um, was the possibility of exposure to, what do you call it? Um, what's Yeah, exposure of UV rays, of the skin, to human skin, to UV rays, which can cause what do you call it? Skin cancer, right? But then there may be other effects that will be in the mark scheme. So you can take note of those ones. Okay, so okay, here they confirmed something that we just said now. Carbon dioxide is a greenhouse gas, true. It now says figure 3 shows the percentage of carbon dioxide in the Earth's atmosphere from 1750. Wow, that's a long time. Okay, so you can see clearly that 1750, possibly we did not have, that was not the age of industrialization, right? So when industry started coming into the picture in terms of mass activities, commercial activities, you can see that the concentration of carbon dioxide increases way up. And I think that should also have been contributed from um, man's activities, cutting down trees and stuff like that. It now says, describe the trend in the percentage of carbon dioxide in the Earth's atmosphere from 1750 to 2000. Is there anything to describe here? It's clearly increasing. It's increasing slowly. And you can cite the fact that in 1750, that was before the time of industrialization. And, industrialization where mass activities, industrial activities were non-existent, or, then at the point of industrialization, it started increasing. And of course, industrialization also came with um, more uses for wood, for living and all that. So that also caused cutting down of trees, which would have absorbed the carbon dioxide from the atmosphere. Okay, so did that make any sense? Did you get anything from that?
Yes.
Okay, so moving on. It says determine the change in percentage of carbon dioxide in the Earth's atmosphere from 1950 to 2000. So where is 1950? 1950 is here. Let's see. 1950 is here. So if we trace it to the axis, to the graph, sorry, that would be here. And that would be uh, 0.030. Then 1950 to what? Was it 2000 they said?
I think so.
Okay, all right, let's assume it's 2000. So I'm
I see
tracing it up to 2000.
0.36.
And
So 0.
yeah, 0. So if you subtract that, what would you get? 0.36 would be 0.006,
Yes.
isn't it? Okay. All right. Okay, 0.006. Okay, yes, it was 2000. Okay, so you just put your values and subtract. No. Okay, they said change in percentage. Yes, yes, it's correct. Yes, 0.006. Okay. It now says give one reason why the percentage of carbon dioxide in the atmosphere is changing. So why do you think? I think I've given several reasons, right? Industrialization. What else? Deforestation, more deforestation efforts, and yeah, those are two reasons. So you can choose anyone you want. And of course, I even talked about another one. Cars, most cars that were invented and to use fossil fuels were also not really existent by 1750. So invention of cars and machines also came into the picture to contribute to the rise in percentage of carbon dioxide in the atmosphere. And of course, you can also allude to the fact that human population is also on the increase, right? That's also another possibility. Okay, so the next one says, predict the percentage of what? Carbon dioxide in the Earth's atmosphere in 2050. You said you should predict it. Is it not possible to read it from the graph? Oh, they said we should predict it. So if we were to predict it, we have to extend the graph upwards, right?
Yes.
So maybe your ruler will help you a bit in that case, if we were to predict it. And then wherever it touches the the line for 2050, then you can read it off from let me see if I can just do something there to show. Okay, so sorry, I was not supposed to. 2050, right? So let's see. All right, that's what I wanted to do. I wanted to just draw something. Okay. So just imagining that your graph went all the way up there. And I think I've touched the line for 2050. So this is the line, right? And it goes all the way up here. So I think to predict it so that we don't have to start calculating values on the y-axis, I think it's safe for us to go with 0.046, right? Hello, Noah, do you agree?
Yes.
Okay. Okay, so I think 0.046 is a safe estimate or prediction. Okay. Okay. Okay, it's the next one says, this question is about the atmosphere of Earth and Mars. It says Earth's early atmosphere may have been like the atmosphere of Mars today. Why are scientists not certain about the percentage of gases in the Earth's early atmosphere? Okay. Could it be because there were really no means of detecting those gases and measuring them that early, about that time? What do you think?
Um, for 4.2.
Yes. No, 4.1, not 4.2.
Oh. Um, limited evidence.
Limited evidence, yes. So, of course, ways of capturing those values was not there. So, yes, I think we'll go with that. Okay. So, if we stopped at 4.2, would that be okay for you? Would you be able to handle the rest?
Yes.
Okay. So when we're done, right, please help me send the mark schemes for this one and the one that we finished earlier. You could send it via WhatsApp.
I should send what?
The mark schemes.
Okay.
Yeah. Just help me with the mark schemes so I could, for reference later. Okay, so the last question we're considering is, what was formed from the water vapor in the Earth's early atmosphere? Okay, obviously, we know it's oceans, right?
Oh, yes.
Yes, it's oceans. Okay, so. Yeah, we did a good job. I think you would be able to take it up from here. All right, so the exams are going pretty well. Um, I think the next one is physics, right?
Yes.
Okay. Wow. And just like that, it's almost a wrap. Yeah. Okay, I've seen the papers you sent, the mark schemes. Thank you. Okay. I'm sure you're going to have a very big, you're going to take a very big break after the whole exams. It's not
Yes.
easy, but it's worth it anyways. Yeah, it's worth it. Okay, that's interesting. So physics will be next week. Oh, okay. So chemistry is not actually tomorrow. It's actually the day after, right?
So on Friday, yeah.
Okay.
And then
Okay. So let me see. Oh, I was thinking
chemistry's
it
on
was
Friday,
tomorrow.
physics is on Monday.
Oh, okay. 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 Physics is on Monday, right?
Yes.
Okay. 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 So okay, so we'll still have a class tomorrow, right?
Yes.
Okay. Okay. Then Saturday and Sunday. Okay. All right then. Enjoy the rest of your evening.
Thank you too. Bye.
Yeah, bye.